So maybe at this point you've noticed that a lot of the problems we've been thinking about are kind of surface integrals that you weren't asked to do before. So even when we looked at this familiar shape, you would have only been asked to look at the surface integral of the top part and ignore these side parts. Um, and so this divergence theorem is solving a problem that you would normally have to do. Same with this hemisphere thing. And there's kind of two different things going on here. First of all, you were never asked to do surface integral over something like this because it would be just a lot of work. You would have to set up four different surface integrals. For the hemisphere one, you would have had to set up two. And so you reasonably could be asked to find surface integrals through a closed surface. And a lot of real life things are closed, so it comes up quite often. But supposing you wanted to think about an open surface. Sort of divergence theorem is for closed surfaces. But you can use it during open surface problems. And kind of this is the approach. So identify a closed surface related to your open surface. Use divergence. And then subtract surface integral for extra parts. To create open surface again. So thinking, for example, about this problem we just did. Let's call that S1. Too similar. That S2. And that S3, the three different wedgy corners of the triangle. And then here's our normal. S4 is going to be that slanted part, x plus y plus c equals 1. So the closed surface we looked at was S1 and S2 and S3 and S4. And you can do the divergence theorem over that entire surface. But we know that flux integrals can be combined as like sums. So the flux integral over the closed surface is the sum of the flux integral over all the separate little surfaces I labeled. And so if you really wanted to know the flux integral through just that top part, you could go ahead and use your divergence theorem for the entire surface and then subtract off individual flux integrals. And I don't really have room here, which is why I'm doing the dot thing. But you would take your entire problem we just did, and then you would subtract individually the flux integrals out of surface 1 through surface 3. And you don't have to remember like all these equations I just wrote down. It was just to talk about the approach with you. And we'll actually do an example that kind of shows this idea. So we're going to imagine that we wanted to evaluate the double integral, sorry, the surface integral, f dot n ds for f equal to xy 0 minus z squared over the upper 5 faces of the unit cube. And so what this is, x, y, z, is here's the unit cube. For 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, 0 less than or equal to z less than or equal to 1. I guess I should have drawn that a bit better. So there's the cube. And we're thinking about the upper 5 faces. So those three that are facing us, and these 2 behind us, kind of like blocked by the front faces. But we're not thinking about this bottom face. So this is an open surface. And we can call that bottom face S6, I guess. And so our approach here is that I still like divergence theorem quite a bit. So I'm going to evaluate the complete closed cube would be the surface given to us, the upper 5 faces, plus that empty S6 that we're not using. And I can go ahead and use divergence theorem on that one. And then if I want f dot n of my surface S that's only those 5 faces, then I can go ahead and look at that divergence theorem result. That tells me flux through all 6 faces. And then I can just subtract the surface integral over only that 6th face. This is a little bit more work than just the divergence theorem, because you do have to evaluate a surface integral at the end. But if you didn't use the divergence theorem, you would have to find all 5 faces separately and then add them together at the end, which would be more integrals than what we're talking about. So that's the approach, generally speaking, and then specifically applied to this example. We'll go ahead and in the next video work through the details of this. I think that we'll run a bit long if we do that here.